We're in the middle of a blizzard. See, there was a negative impact there, but I did a lot of flyers spent. What's the best I could do under those scenarios? So, really quick and easy way to actually interact with and use a model and get some understanding of what it is. But what's really interesting is actually looking at the model itself. So here's the raw output, the raw analytical model that was found, right? And what's interesting is this is what I want to point out here is these are nonlinear time series features that are automatically found from the data, right? So we're able to determine that, hey, similar thing with your flyer production costs. It's not what you're doing today. This is delayed by 1 week, and it's averaged out over 3 previous weeks, right? So the flyers you're producing, you're spending, you're pumping out today are having a blurred effect, right? And until you account for this, you would probably never find that there's this sort of correspondence between your marketing activities to what's actually happening in the physical stores themselves. So it's being able to find these effects that you wouldn't normally be able to detect on your own. In fact, these guys thought that, hey, flyers are probably a good idea to be doing, but they actually had no way of actually interpreting it. This is one of the major structural features of predicting the differences in the margin. Similar here to, here's the open rate for their emails. In this case, it's multiplied by the click rate for the emails. So that's saying that, hey, emails, the open rate, you have to get emails that are being opened and being clicked on. It's not enough just to send out the emails that get open. And then also, hey, there's this negative impact on the weather. So all these are positive impacts, except for the weather had this negative impact. You'll get a sensitivity analysis. The final thing I want to show you here is, and Dave mentioned this in his talk earlier, is if you're going to solve a big challenge in the data set, a big problem, usually the data that you have is not enough. Right? You need to be able to marry that with some domain expertise to actually solve one of these problems. And to give you an example of that, you might look at, hey, the variable here is the flyer production costs. Right? How much am I spending on flyers? Is that really the signal that's driving the change or the moving the needle on the margin order for these stores? What you can do is actually click into this and look at what else is really closely related to that. In fact, there's almost one that's almost identical, which is not just the flyer production costs, but how big are these flyers? How many pages do they include? Really, what these guys found was, hey, the more things we're putting in there, the more impact there is. So there's an opportunity for them to actually have more pages included in their flyers, and ultimately have a large impact on their sales effectiveness. Right, so these are things you might otherwise not find at all. So we're not trying to claim that, hey, the flyer production cost is the key signal here, but there's something really special about the structure that's giving you that accuracy. And it's one of these few things. It's either your costs, your total pages, or some of these other really closely related quantities here. But these are the types of things that will automatically pop out. In fact, the way that we capture that information from the users, letting them iterate on the results. So what you could do here is go and say, hey, block this variable. I don't care. This is not the thing that's actually causing it. I'm going to give you some of my domain expertise that you wouldn't have known if all you had was the data. And let the computer, basically the machines, update all the patterns. Here's the next best thing to allow you to sort of peel the onion and dig deeper and deeper into, ultimately, the holy grail, which is what are the causal impacts on the data set, the thing I care about. Right? So this is a really quick whirlwind tour going from a raw data set that we really knew nothing about. Right? We knew it was somehow sales related, retail related, all the way to a potential causal reasoning impact, the thing you could actually change, have a large effect on the success of a business or a business application to solve a problem. So that's a really quick tour of that episode. So let me finish up here with just mentioning a few more different applications that we've seen out in the wild that I think are kind of interesting, right? So one of the major companies that we work with is CVS. And one of the challenges they have is interpreting and understanding demand for different prescription drugs. In fact, these are people that, if you are prescribed a drug, it needs to be approved. And there's laws saying if there's a certain delay in how you approve these drugs, if you don't have enough people to inspect and analyze them in certain ways, you get fined like millions and millions of dollars. So these guys end up having 10 times as many people, staff, to approve these drugs as actually necessary. And their error rates were enormous. They were like 60 or 50% errors in estimating how many people they're actually going to need to approve these drugs, right? So one of the advantages we had there is we can detect when things go generic, how that impacts the rates that these things get, different drugs get prescribed, and all the regulatory effects will also impact the frequency that a drug gets prescribed to a potential patient. And that basically let them go down to like something like 4% error. And they're end up saving like millions of dollars a week just by using a cognitive system to help them understand when the demand for drugs is going to change. Similar story with Audi, where they're looking for, how do you select what types of cars do I ship to what locations, which ones will actually have a higher impact on my sales. Things like black cars don't sell as well in the South, right? And what they're doing is because they get hotter, right? Or black interiors are just less common in the South. But if you're in Minnesota, they're very, very common. But if you look at these companies in the state they're at, they have all this information to figure this stuff out. But they haven't been able to do it because, to be honest, the best data scientists in the world are really not going to some of these stores like CVS, Audi, or Bex. They're going either to Wall Street, or they're going to Google or SpaceX, or these really sexy companies. And allowing these people to sort of unlock some of these low-hanging fruit through software is a really high impact, where they can go, basically Audi went from having a model to try to anticipate demand across the entire US to now a location-specific prediction, prescription for what's going on, what they should be doing. All the way up to sort of Bex, which is a hybrid seed, a corn seed manufacturer, where they plant and they breed tens of thousands of different breeds of corn to have better resistance to drugs, to be more nutritious, all these sorts of things. And one of the challenges they have is they don't know a particular breed did really well this year because it was in a really favorable spot on a field, or there's something actually intrinsically good about that particular breed of corn from the data it has. But these guys have invested enormous amounts in basically Internet of Things, of sensing what's going on in all thousands of different cornfields and different locations in them to actually understand what's causing these corn breeds to do better or worse than their neighbors, right? That type of thing. And they're using Eureqa basically to power all of it. And here's some of the visuals of how this stuff gets explained and interpreted back to people through our software, Eureqa. And for us, it's sort of critical to not just give a prediction, give an answer, but actually explain it, visualize it, and interpret what's going on. And that's our unique position in the market. So to wrap up here, the higher level concept here we described around machine intelligence, our favorite term. It's basically about extracting meaning from the data, interpreting physically what's going on, going beyond sort of pure prediction. And there's been a lot of early adopting companies, sort of pioneering companies. Dave mentioned a few, Google, IBM, to be able to do this sort of stuff. But this technology is actually readily available today, right? And more and more companies are actually starting to leverage and use this now that AI has basically sort of proven itself out. And there's just many, many new applications ahead of us. So that's all I have for today, so thank you very much.
Talking about using sine, cosine, etc. as a building block to search out the formula for the data graph. And you said you were not just doing a broad search, but honing in on the partial results so far. It sounded like hill climbing, and I was wondering, and using multiple starting search points here to collect the local minimum. And I was wondering, to what extent is that correct, or more importantly, is there a paper or papers published that do describe that search process across the space? Can you summarize that in some way, but especially the references, if any?
Yeah, absolutely. So if you search for my name in Cornell, you'll find a number of papers, especially the one in Science. I think is a great explanation of how this stuff works.
Okay.
I was going to give a high-level overview, a sort of anecdote for what that's like. Imagine you're playing Yahtzee. Have you guys played the game Yahtzee before? You've got 6 dice, you roll them, and you're trying to get all the same number. So one approach, say you're trying to get Yahtzee, you can just sort of throw all 6 at once and see what you got. Did I get Yahtzee? Yes or no? Pick up the dice, throw it again. You can do that tons and tons and tons of times, hoping that you get Yahtzee. A much better approach would be to throw the dice once, and then say, hey, I'm going to pick a number. I'm going to pick 5, and I'm going to roll 1 dice at a time now. So I'm going to pick up 1 dice, roll that one until I get a 5. pick up the next dice, roll that one until I get 5. So there's much, much more efficient ways of getting ultimately to all 5s if you do it individually. But if you try to do it all in one shot, basically with the dimensionality of the data sets we're talking about now, it'll take you forever. You'll never finish. So that's a sort of high-level anecdote. And if you talk to me after, I'll give you a list of some of the papers to check out and how you actually create these models efficiently. Yes?
But you mentioned downloading the software from the site. What can we actually do to play around with the software?
So we have an online system that you can basically log into, connect data to, and then start analyzing for patterns. So it's all accessible on our website if you want to check out and find out more information. Yes, right back there.
When you spoke about chess and with Deep Blue and you said that it doesn't give the explanation, in the pendulum example that you showed that you're using your algorithm, it shows not the explanation, but the algorithm of the movement. It doesn't explain how it works. It doesn't teach me physics like it doesn't teach me chess. So what's the big difference?
So I would argue that's a very precise description of physics that are going on. In fact, without having a full-blown natural language processing type of engine on top of that to interpret and explain back what that equation means, that is as good as you can possibly get. It's the most accurate, precise description of the system because it corresponds to how the thing is put together. It predicts how it'll move. It's really the most elegant sort of way of describing the system. That's why sort of science is bootstrapped up using math as a language to describe things. But you're right. To a sense, it's in that case still a formula. So we've actually been investing in a lot of technology in this user interaction and actually go out, all right, what is that pattern actually telling me? So that's sort of the next challenge that we're sort of focusing on. I think we got to solve. All right. Yes, go ahead.
So I think one thing that's missing from a lot of discussions like this, like we hear about machine learning all the time, but we don't actually hear what it is and what it isn't. So if I'm doing a simple linear regression, is that machine learning, or does it require some iterative component to the algorithm, or is it more about the process that you apply that model with sampling and cross-validation and things like that? So I guess if you have a simple rule of thumb, what machine learning is and what it isn't.
Oh, I love this question. So, I mean, traditionally, there's always been this huge divide where statisticians on one side and then machine learning people on the other side. And from my perspective, these people are doing really similar things. They're making estimations from the data. So I would classify all that sort of stuff, linear regressions, generalized linear models that statisticians have been doing forever. Machine learning people are using those today. Like cattle competitions are being won using simple linear regression, things like this, or very, really simple techniques that have been known for a while that aren't really complex, sophisticated algorithms, right? So to me, those are one and the same. But if you think about, a lot of people ask about, there's even more confusion around artificial intelligence, I would say. And I would blame people like Stephen Hawking, Elon Musk for sort of causing a lot of interest and a lot of stir, but sort of mischaracterizing, in my opinion, right? So really, artificial intelligence is a really broad field. It includes machine learning, it includes natural language processing, right? It includes cognitive computing. It's really the umbrella term for machines doing smart things. And machine learning, to me, is really the subset of AI that is really the collection of algorithms, right? It's the different approaches, different ways of analyzing things, right? Regressions, optimizations, decision trees, SVMs. These are all things that naturally roll up under machine learning to me, right? And then other people are now carving out things like cognitive computing, machine intelligence, and that's actually it's a little more nuanced, right? It's sort of somewhere between like what we think of as AI that's smart on its own versus machine learning, which is really sort of the subset of algorithms, the tools that a lot of systems are built on. But it's a great, interesting thing to see that the sort of understanding evolve. So a lot of when I talk to people, I was trying to demystify what some of these things mean, but I don't think everyone totally agrees yet, but that's sort of my understanding, at least historically, from what I've learned. How about way in the back there?
Did you ever validate your predictive model for that example?
So that's actually a physical system. Like you can go open a textbook and find the right answer, right? So we were able to find that through basically analyzing motion tracking data, that system. We can actually go back and look at it.
Right, or I mean the sales one. The
Oh,
sales
yeah,
one.
absolutely. So I can't talk too much about it because that was real data. But actually, they went in and verified, like, hey, when we make these sort of changes, if we spike something, they've done certain tests, they actually see a corresponding spike. So one of the examples that was kind of interesting was they looked at, one of the major trends that popped out on this data set was, if there's a spike in building supplies, like this happened to be a home improvement chain, about 5 to 6 weeks later, there'd be a corresponding spike in painting supplies. Right? It's a very natural trend that that naturally fell out of the data that I think made a lot of sense in retrospect, but they were able to find it on their own, but popped right out from the machine. And I would also treat, like, cognitive computing in general, we're able to find these things and to an extent interpret them and understand them. But ultimately, it's still a hypothesis. It's the best theory possible given the data you have. I think it's critical to actually go back and now test these effects. Is this real? Use your domain expertise and actually put them into practice and see. Right? Because you can always potentially be fooled, but you can use machines actually to really quickly guide you to really the most likely factors to focus in on, right? Which you may never have had a compass to look at before. Yes?
Thank you for showing all these cool things. If I want to learn more about machine learning or like AI or whatever, do you have any good resources or tools to recommend if I want to learn how to build something like that or to learn more?
Absolutely. Talk to me afterward, and I'll try to give you some tips on how to learn more about machine learning, maybe even get involved in building some of these systems. Yeah, absolutely. Yes?
Hi. About a year and a half ago, you presented at Part2, and,
Yes.
and I remember somebody described this as being symbolic programming, and I don't know if it is or isn't, but could you kind of help us say something about that?
Yeah, so the broader field here is known as evolutionary search. Where you're trying to take a bunch of building blocks and construct them in a really intelligent way to describe something. So one of the broader fields is symbolic modeling, where you're actually trying to identify what symbols do I use. So this actually falls within that subset. One of the challenges, this has been an interesting sort of academic interest to be able to run these types of algorithms probably over the past 15, 20 or so years, but only recently actually have we been able to solve it on real world problems. Like examples where there's hundreds or thousands of variables. So that's sort of been sort of the breakthroughs in making these things scale, and not just building models that fit the data, but actually fit it in the simplest, most meaningful, interpretable way. So that's been a new type of optimization that just has not scaled very well before. So that's been some of the breakthroughs. Yes?
So one issue with machine learning algorithms is they need a lot of data, particularly the neural networks. Can you characterize how much data you need for these, and also how do you handle overfitting?
So the question was, how much data do you really need, right? And how do you handle things like overfitting? And we were talking earlier about, Dave made the comment about, hey, you can actually do a lot with small data sets. So one of the funny stories was one of the first customers I worked with was the US Air Force. And I remember getting on site, they were exploring and analyzing the data with Eureqa, and they said, we have this huge data set. It's one of the biggest ever collected. And then they opened it up in Excel, and it was about 100 lines in Excel. But then they explained to me, hey, every single row in this data set probably costs about $10,000 to $50,000 to do that experiment and collect that row of data on that example. They were optimizing materials that have certain properties for their aircraft. And it's surprising what you can do with a limited amount of data. A lot of people don't think they have enough. In my experience, typically, if you have on the order of a few dozen data points to a few hundred, you can start to find some interesting things there. But it's not really the number of rows or examples that you have. It's really about information that's in the data set you have. So you can imagine having the same data point repeated 100 times. That's really not going to help you. It's really, is there enough variation in the data set to give you an interesting effect? So I definitely had experiences where people thought, particularly for like you're anticipating sales at a store, hey, this thing should be really important. This variable is the one I worked on. Why isn't it showing up as having an effect? Well, the ultimate answer ended up being, well, the thing you had, you always had it in effect since you started collecting data. You've never changed it. So there's really no information there to determine was that impactful or not. So it's really about, has there been variation, have there been things changing, and those are the things you actually measure, reason about, and show evidence for having certain effects. Ultimately, how do you handle things like overfitting? This is where having more data helps a lot, and reducing complexity of your ultimate models helps a lot as well. But ultimately, the simplest approach is to use very rigorous cross-validation. So you need to train very strictly and test models in phases and have different sets of, here's how I optimize it, here's how I find the structure, here's how I tune the coefficients, here's how I select the very best models, here's how I actually assess how well they'll do on throwing new data in the future. Other approaches actually there's some statistical approaches, but they're more involved. Usually cross-validation is the most powerful thing that people use. So if you look at people doing machine learning competitions and things like this, all of them are using cross-validation in some form or another to validate that they're not overfitting and prevent that sort of thing. But it's a very open-ended question, right? There's always that possibility. Yes?
I have two questions. Is sparse matrix the only requirement to use Eureqa? And my second question is, do you think machine intelligence can get or discover quantum physics?
All right, so the question was, really, what structured data do I need? And can these things actually decipher really advanced topics such as in quantum physics? Right, so one thing I should point out is there's been enormous progress in cognitive computing to be able to analyze unstructured text and data analysis, stuff like that. That's one thing I would say that Eureqa just does not do. So we focus almost exclusively on structured text, so matrix form. We can handle some things like categorical variables and automatically interpret and explain those, but typically we steer away from sort of raw text analysis that a lot of other people have made way more progress on than we have. We've been focused on really business data where you're measuring things over time and you want to understand the impacts and effects. And the question is, could you use this type of approach to machine intelligence to make new profound discoveries? So I'll go back to the example where I think people are already doing that, right? So the simplest example is in math. Like I'm talking about mathematical research, like discovering mathematical patterns. People now, there's a thing called a computational proof, right, where they can exhaustively test inputs and then conclusively determine that, hey, there's no other explanation for this mathematical curiosity or whatever it is. Crazy people from that. The other aspect here is people are already using Eureqa in their research, right? So if you go to Google Scholar and you type in Eureqa, but with a Q, not the K, so you get the software, there's about just under 600 citations where people have published research where they cite us in the results of their analysis, which is kind of cool. And it's been everything from like medical applications, like determining warning signs for macular degeneration, to improving the accuracy of appendicitis detection in children. And I've even seen some applications to cosmology and things like this. So there's been a lot of interesting applications people are applying this to for the first time.
But quantum physics is a weird animal.
Oh yeah, totally. So quantum physics is its own beast. But I think if you frame the data in a way that you could actually think about a lot of different variables and different explanations, I think that could be applied, right? But we have to think more about it. I don't have a great answer for some of the esoteric things in quantum physics just now. Yes, go ahead.
Could you handle data sets that have discontinuities in them? Like two different modes of behavior based on the state of other variables?
Yes, so the question was, can you handle hard discontinuities in the data? Right, so it's all based upon what building blocks you provide to it, like having sine or cosine. So one of the building blocks could be sort of if-then-else statement. Right? Is there sort of a break or a split? Or maybe there's some threshold effect that takes place. So it's a function of what's your library to describe those things. If you give those operations to it, you'll be able to find the sorts of patterns. The other case where we see a lot of discontinuities is, this is a sales example where we're looking at one time series. One of the applications is to imagine throwing all of your stores in there. So you have multiple time series in the same data set. And it's sort of like a time series with a hard break, so discontinuity, and then a new store starts, at a new date that goes into the future. So those are all things that, the software uses automatically handle, so it's not looking for delayed effects across stores and across different communities like that. But yeah, those are things that sort of you can naturally find and automatically handle. Yes?
If your the data you're modeling is a stochastic process, how do you test for that, and then how does that get handled?
So the question is, how do you handle modeling like stochastic systems, right? Things that are produced purely stochastically. So we don't have native support for this yet, but one of the papers I have looks at a building block that's a stochastic building block, right? So it's sort of like saying in your mathematical expression, there's going to be some stochastic input to the system that you can't control. It's almost like inventing a random input. And we can actually model the envelope or the output distribution based upon these randomized effects, these randomized building blocks that could appear in the model. But it's more advanced, I think it's more involved. In practice, I think what people end up doing if there's a stochastic process is, if you use enough data, you'll be able to find the general trend of that stochastic process. So like an example might be Locke-Volterra's, or like a sort of predator-prey model that's inherently just a stochastic system. If you want to properly simulate, you have to use, what's it called, the Gillespie modeling or stochastic modeling like that. But on higher populations, there's actually a very smooth, approximately smooth effect. You can very, very accurately model without sort of stochastic elements to it. So I think in most of practice, most people ignore the stochastic variation, but they end up looking at what do my residuals look like to give me sort of confidence intervals. But usually...
Can you identify that, though?
So in the research thing I was just talking about, that paper, there's people looking into that, but not today, not yet, that you can download. But I think that sort of thing is coming. Like it's another sort of challenge to be able to describe and capture. Any other questions? Yes?
Can you tell us a little bit more about a technique that is used in identifying which variables are interesting to predict?
Oh yes, absolutely. So the question was, how does it work for detecting which variables are interesting to predict? So there's some things in the data that will clearly indicate this variable is not interesting to predict. Like if it's 90% missing, it's unlikely to be one of the things that you're actually interested in forecasting in the future. There's some other statistical properties of how stationary is it? It would be useful to model this, or you're going to be fooled very, very easily. You're going to morph into it. But ultimately, it comes down to how well can you predict this into the future? So on new data, how accurate can you get predicting this thing? So that's the first criterion. If you can't predict it, then we basically reject it, or we rank it very, very lowly. Like, hey, don't spend a lot of time on this because it's not something you're going to make much progress on to get high accuracy. The second factor is, even if you can predict it, how interesting is the model you need to have to actually predict that system? Is it trivial, or is it just some simple linear correlation? So if it's trivial, like say it's just a simple linear correlation, you probably already know about it. Right? You can just look at the list of covariates and see that it's probably the things you already know. The stuff that's interesting is stuff that's non-obvious, it's non-trivial. Maybe there's some non-linear effect. Maybe there's a delayed effect that's going on. So that's the other criterion that you use. So you have a number of sort of statistical criterions, criteria combined with how accurate can you model it, and is it trivial or not. That's how we go about it. But if you're curious on more details, I can show you more later. Yes, back here.
Can you talk a bit more about how you handle data conflicts? Like you mentioned a certain segment in the north would be fine with a black interior versus in the south would for light colors. Is there a segmentation that happens internally where you can separate out entities within the data based on that, or is it lumped together? Or how do you handle that?
So the question is, how do you handle like natural groupings or segmentations in the data that might be location specific or preference specific? So that gets back to what's the language I can use to describe and build models. So I have operations that allow me to capture different groups. So one way you could do it is you could have, going back to a math example, is it in group A, sort of 0, 1 multiplied by some effect, some model A. Combined with, is it in group B times whatever the model is for group B. So there's natural ways of finding that. You could bootstrap out that segmentation basically from the data and from the basic building blocks in a mathematical model. But it's slightly different. You might be more familiar with like a clustering approach, so it's sort of directly look for those groupings. That's one thing we've explored in terms of being able to naturally detect those clusterings and give that as a new variable, sort of bootstrap up these clusters and groups from the data. But it's not something we've completely automated yet, but it's an interesting application. I would say in practice, what we see happening is a lot of people are already doing some modeling across maybe everything averaged together, right? So then you end up predicting sort of the average effect of all of the stores at once, or all of the machine parts I make, or all the production parts or SKUs. But because it's so easy to just throw data in, build models, and see the outputs, they just basically say, you know, model every single store differently, right? And then summarize the results back for me. So it's, they end up sort of looking at those in isolation on their own and looking at differences there. So a lot of times they already have an idea of a grouping they actually care about or look at, and that's what tends to drive the use cases that I've seen in this. Right behind you, yes.
Sorry for a very technical question. So I don't understand why accuracy and model complexity have to form a Pareto front unless you enforce them by definition.
Unless we force what, Cindy?
Enforce the Pareto optimality by definition.
So the idea is, you can imagine you could add more and more variables, more and more degrees of freedom. That's going to increase your complexity, and typically it's going to give you a model that's easier to bend towards the data. It gives you higher and higher accuracy, right? So there's a fundamental trade-off between how big and complex something is versus how precisely can it model individual fluctuations of features in the raw data on its own. So a really, really simple model can't capture a lot of variation, but a more complex one can. But there's some trade-off where you get too complex and you start to overfit the data, right? So there's some point where it doesn't make sense to be getting more complex.
Is that really true for high-dimensional data? Isn't that actually the other way around? When you explore the dimensionality, you have multi-collinearity, there are noisy data points, you have irrelevant variables and so on. So you increase your complexity and your accuracy will drop.
So that was the point I was just describing. So there's going to be a point where you start to overfit. You get tricked by things like covariance and collinearity and these sorts of things where getting more complexity, more variables in there actually can potentially hurt you, right? So it's important to sort of explore that space, and using accuracy and complexity is just a way to sort of filter down into, you know, how far can you get with the data you have.